I guess we can start now that you walked in. Last time we talked about some basic network terminology, and I'm going to continue with the network flow problems today. We have limited time, 2 hours today plus 1 hour next time, which means that I have to sort of squeeze in lots of information into a small time slot. So try to follow closely. Don't be too busy writing down all the time, because the arguments on the board will be probably important for you to absorb the basics of the material. So let's look at the node arc incidence matrix first. I'll refer to it by A. We want to write down the minimum cost network flow problem in the following form. In the more general case, X will be greater than or equal to L, less than or equal to U, but this is the more specific case. AX equals B refers to the node arc incidence matrix of a given network. So we're going to define that and see what happens. But this problem simply is a compact representation for the following problem. Minimization of the cost times the flow amount in arc ij for all arcs. This is a strict script A, stands for the set of all arcs of a given network, subject to the total outflow xij summed over j, for which ij is a defined arc, minus xji summed over those nodes j, for which ji is a defined arc, equals the right-hand side value, bi, which, if positive, means node I is a supply node or a source. If negative, if bi is a negative number, then node I is a sink or is a demand node. And if bi is 0, it's a transshipment node. Okay? This is written for each I in the node set, script in. And xij's are non-negative numbers for the arcs. So C stands for the vector of costs associated with arcs. So C has as many components as you have number of arcs. X at the top stands for the vector of xij's, ordered in the same way as the members of C vector. A refers to the matrix you see on the left side of the flow conservation equations. And we're going to focus on that here. And this is it. So this is the compact form of what you see in open form here. Now here, suppose the original network with node set N and arc set A has, say, M nodes numbered from 1 to M. And let's assume it has N arcs numbered in some way. Okay? So my A matrix, the node arc incidence matrix A, has M rows, each associated with nodes, and it has N columns. Each column is associated with a particular arc, or with a xij variable. Xij variables are the flow variables in the arcs. Okay? So let's denote by Aij the arc of A, or sorry, the column of A associated with arc Ij. If you look at the arc here, this is the arc we're talking about. There's a flow variable xij here. Of course, there's also the rest of the network here. Now, when you look at the node flow conservation equation for node I, xij will show up as an outflow in that particular equation. Okay? But when you look at the flow conservation equation for node j, which is another equation in the system here, this will show up as an input or inflow. So the inflows are negatively signed, outflows are positively signed. For that reason, Aij will have a very particular structure. It's going to have zeros everywhere, except there's a 1 in one position, which corresponds to row I, or corresponds to node I. And then it has a -1 in some other position corresponding to node J or row J. Elsewhere, it's all zeros. In other words, it doesn't touch any of the other nodes. Arc Ij touches only node I and node J, so it has only a +1 and a -1 in those proper positions. So let's look at an example problem here. I think this is the same example that I gave you before. So for this one, my A matrix will have 1, 2, 3, 4 rows corresponding to nodes. And then it's going to have columns associated with the arcs. 1, 2, 1, 3, 2, 3, 2, 4, 3, 2, and 3, 4, and 4, 1. So in the first column, we have a +1 and a -1 in positions 1 and 2. Zeros elsewhere. For the second one, we have 1 for row 1, a -1 for row 3, zeros elsewhere, etc. You can see the pattern here. This one has 1 here, -1 here. Of course, the plus and the minus will be upside down. That's quite acceptable. And then we have +1 here, -1 here for 3, 4. And for 4, 1, we have +1 for position 4, -1 for position 1. All right, so that's your node arc incidence matrix. And the constraints of the problem simply says that the sum of the variables that are picked up in the first row add up to B1. So when you look at the system AX equals B, you're simply looking at this times x12, x13, etc. I'm too lazy to write them all down. x41, the last variable. It's got as many components as you have columns here, equals B1. What were the numbers we had? B1 was 4, I think. B2 was 2. B3 was -1. B4 was -5. That's what I remember This is balanced, so we have 4 here, 2, -1, and -5. This is precisely the flow balance equations we wrote down before. Okay? All right. Let me just fill this in because otherwise we may have difficulty later when you study. All right, for example, if you look at the first row times this column will pick up x12 and x13 with plus and x41 with minus, and that adds, they give you 4. Okay? That's precisely the flow conservation equation for node 1. Okay, this is important because we're going to work with this matrix. We're going to work with basis matrices of that. So we need to know, how to identify basis matrices, etc., to be able to find basic feasible solutions, etc. Okay? All right. The first thing to notice is if A is m by n, m nodes, n arcs, then the rank of A is less than or equal to m minus 1. So 1 less than the number of nodes. The reason for that is, well, if you look at this particular one, you can see that immediately. If you add up all of the rows, you will get the 0 vector. Why? Because each column has a +1 and a -1 and zeros. So when you add them up, +1 cancels with -1. You've got zeros elsewhere, so the sum of the rows will give you 0. Because, well, you can write that down. For that reason, the rank is certainly 1. It's not m, but it's less or equal to m minus 1. It turns out that the rank of A is actually equal to m minus 1. That requires a proof, or at least a justification. And maybe I'll give you that justification right now. So let's assume we have a tree. Let T be a spanning tree of the network that induces this particular node arc incidence matrix. And let's just isolate the columns associated with the tree into a submatrix A sub T. So A sub T is the submatrix of A consisting of or corresponding to T. What do I mean by corresponding to? Whichever arcs are in the tree, you pick those columns and put them in A sub T. Any arc not in the tree, you just leave it out. That's what that says. Okay. So what's the size of this? It has m minus 1 columns and m rows. Okay? I'm going to show that A sub T has rank m minus 1. And if you show that, of course, since this is a submatrix of A, then A also has the same rank. Okay? All right, how do we show this? Well, let's do it this way. Let me just illustrate this in the following way. When you look at a tree, the rest of the tree is here. When you look at a tree network, there's a property which says that there's at least one node, actually 2 nodes. There are at least 2 nodes of a tree that have degree 1 each. Degree is defined by the number of arcs that touches a node. Okay? Now, this arc could be this way or the other way. It doesn't really matter. But there's a node of degree 1. There are at least 2. So I pick up I1 as my first node to, say, color. In other words, initially assume all nodes of the tree are uncolored. And then I'm going to color them one at a time in a given order or in a certain order. And that will tell me how to arrange the columns and rows in A sub t. Okay, it's important. So I'm going to pick some node of degree 1 in the initial tree, color it. So let's just color it, for example. This becomes colored now, and I call it I sub 1, whatever the node number is. And there's an adjacent unique node here. Why unique? Because there's only one arc coming into it or coming out of it, so there's a unique adjacent here, and we call that J1. Okay, so arc I1, J1 is the first arc to color. So initially we pick a node of degree 1, we identify the adjacent one, we color the node and then the arc as well, and then we drop the colored node and arc. Okay, so that removes one node plus one arc from the tree. And then you repeat the same thing, these steps, with the remaining tree. Except that, of course, when you remove this, now you're going to have something here which, well, not necessarily that one. You're going to have, again, in this tree, this is still a tree because you did not add anything. You just removed the tip vertex. There will be another node here of degree 1. We will call it I sub 2. There will be an adjacent unique node, J sub 2. And so we just color I sub 1, I sub 2, I sub 3, etc. Okay? You get the idea. Once you do that, well, once you do that, we define A sub t with column permutations in the following way. I'm going to put the first column here as I sub 1, J sub 1. That's the first colored arc. And then the second colored arc will be the second column, etc. The kth colored arc will be the kth one. This goes on up to m minus 1. Because the tree has exactly m minus 1 arcs in it. So this goes on like that. And I'm rearranging the rows of the matrix also according to the numbering scheme. So the first colored node becomes the first node, first row. The second colored one is the second one, so on and so forth. The kth one is the kth row. And then we have the m minus first and mth. Now at the end, of course, when you choose the m minus first node, the rest of the tree has exactly one arc, one node left. This is the rest of the tree. There's a unique arc here. So this arc happens to be this one. So J sub m minus 1 is indeed I sub m actually. So when you color this and color that one, there's a surviving degenerate node. So the tree degenerates into a single node. That's the last node. last node, which is not colored. All the other ones are colored one at a time. Okay? So why did we do it this way? Well, the reason is the following. When you look at the first arc, it touches I1. So it has either a plus or a minus 1 here. Okay? Now, the other non-zero element in this column is somewhere here. I don't know where, but it's somewhere here. Okay? And when you look at the second colored node, I sub 2, you identified the adjacent one, J sub 2. So I sub 1 at that point was dropped out of the tree. So it wasn't available for identification, which means you surely have a 0 here. Okay? And you surely have a plus or minus 1 because the second arc here touches I sub 2. And then the remaining non-zero element is somewhere here. Sorry, there's, all right. And you go to the kth one. This one has a plus or minus 1 with zeros all the way here. Because these zeros come from the fact that anything that's colored is dropped out of the tree. Okay, so they are not available anymore. And so for this reason, this just goes on like this, with a plus or minus 1 here at the end, and then possibly non-zero elements in the diagonal here. So this is the way the matrix will look if you do the column and row permutations according to the order in which you've assigned the colors. All right, so what is the purpose of this? This guy has m rows, m minus 1 columns, and the rank of this, a sub t, is surely m minus 1. Because when you add up the rows, obviously they give you 0, so it cannot be m. We argued for that before. But the columns, this is a lower triangular matrix with non-zero elements in the diagonal, so there's no linear dependency among the columns for that reason. Okay? So, and the matrix is lower triangular. So these two imply that the rank is exactly m minus 1, which implies, of course, rank of A is also m, because it's a submatrix of A. Okay? All right. So these things are sort of important. I mean, you know, if you look at certain examples, you would immediately realize that the rank is actually exactly m minus 1, but you need to be able to also prove these things. I mean, you know, somebody already supplied you the proof, and I simply borrowed it from the literature. However, sometimes you need to devise proofs of your own for other, you know, problems, and you have to think of such ways of actually making it intelligible to other people. That's the important part here. Or just proving things just by claiming that they are correct or they are right doesn't work, unfortunately, except for students. A lot of students claim they are right. Okay. All right, so this is important. And that brings us to the topic of basis matrices of the A matrix. Well, first of all, the fact that the rank of A is equal to m minus 1 tells me I need m-1 columns in a basis B of the matrix. And of course, because of the linear dependency among the rows, we're going to drop some row, okay, one of the rows. And these should be, of course, linearly independent. So I need to somehow make sure I have m-1 linearly independent columns in a basis. Why? Because the rank is m-1. From the foregoing proof, you can see that each tree T gives you a matrix A sub T corresponding to columns of the A matrix that are corresponding to arcs in T. And this would be a valid basis because we just proved that it could be put into lower triangular form with non-zero elements in the diagonal. Okay? So it would correspond to a valid basis if you drop a row. Which row do you drop? For example, the last row. Okay? If last row is dropped, for example. All right. Can I have other subgraphs that have, again, m-1 columns or m-1 arcs that define a basis? So the question is there any other subgraph other than a tree that has m-1 arcs in it so that the columns associated with those arcs would form a sub matrix of A having the proper number of columns? Would that give me a basis or not? So would they be linearly independent? That's the question I'm posing here. So here's an observation for you. If a subgraph having m-1 nodes, m-1 arcs, so this refers to the number of arcs in the subgraph, okay? And of course it should be spanning. The number of nodes, well, every node is included in the subgraph, so it's a spanning subgraph, but it has m-1 arcs. This is just a convention for that, okay? So if Gm-1 has a cycle, then the submatrix say A G sub n-1 corresponding to this graph has linearly dependent columns. So whenever you have a cycle, you have linear dependency among the columns. And you need to, if you're asked, you need to be able to show why this is the case. This is a well-known fact by people who are familiar with network flow algorithms. Nevertheless, when you ask them why, many of them, 99% of them, well, maybe 90% of them will not give you a good answer. And so please be among the 10%, not among the 90%. Okay? All right. What is the reason for that? The reason for that is the following. I'll just illustrate it by means of a chain. Suppose you have a chain like this with certain arc directions, whatever they are. Suppose these are the arc directions. Remember, in a chain, you don't really pay attention to the arc directions. All right, so in this case, if you take the columns A14, I'm looking at the columns here, I'm going to assign a clockwise direction to these arcs, and I'm going to, so you're taking a walk, for example, starting at some node, say at node 1. You're taking a walk along the cycle in clockwise direction. Okay? When you take a walk in clockwise direction, whenever you encounter an arc in the direction you walk, you assign, say, plus. Okay? Whenever you see an arc in the reverse direction, assign a minus here. So this one is also minus. What about this one? This is also minus, and this one is, no, sorry, this is plus, because we're walking this way. This is minus, right? So I'm looking at the columns A14 minus A48. I'm using the pluses and minuses to decide what the coefficients will be here. Minus A38. This one is 35 with a plus, and then we have 15 with a minus. When you add them up, you will get a vector of zeros. That's the claim. Okay? Of course, this is an example proof. Okay? But in general, you can always give the same argument for any cycle. Now, why is this 0? The reason is the following. If you look at A14, it has a 1 in position 1 and a minus 1 in position 4. Which means that this is the difference of the first unit vector and the fourth unit vector, because it, because the plus 1 is accounted for by E1, the minus 1 in the fourth position is accounted for minus E4. Okay, so that's my A14. Now A48 is similar. It has E4 and E8, except that I have a minus sign, so this one shows up as a minus here. Let's look at this one again with a minus sign. So this one gives you that. This one is E3 minus E8. Then we have plus E3 minus E5, and then minus E1 minus E5. So I simply took my columns, expressed them as the difference of two unit vectors, and that's the way what you get. I don't know if this is equal to 0 or not, but you can see that if you remove the parentheses, you have E1 here. Well, I'm just going to do it here. You have a plus E1 here, a minus E1 here, okay? So that E1 cancels with that E1. Minus E4, and then there's a problem here. What is the problem?
A4.
This is A4, this is 8-4. Yeah, that's what's wrong. It's 8-4, sorry. Change that. Okay, so minus E4, so this E4 cancels with that one. And then minus E8 cancels with this one. E3 cancels with that one. Anyway, everything cancels with something else, okay? So it gives you a vector of zeros. Of course, in the general case, this is true. In the general case, if you have a chain, say C, a cycle, sorry, not a chain, but a cycle. If you have a cycle C, if you add up the columns A, I, J in the cycle, this is the same thing as adding up EI minus EJ's IJ in the cycle. For those in the plus orientation, so let's call that the plus portion of the cycle. And then for the remaining ones, I should do that also here. Yeah. Let me change this. Yeah. So let's partition the arcs in the cycle into plus marked and minus marked ones, so that we're looking at the columns with a plus coefficient for the plus marked ones and with a minus 1 coefficient for the minus labeled ones. And that will give you this for the two portions. And this gives you 0, because if you look at the ith, say, node I in the cycle, one of three things could happen. Either you have two arcs in this orientation, say plus orientation, like that. In that case, you have something here, say A, and something else here. This is the one under consideration, okay? I'm fixing my nodes. But when you look at this, if this is the arc, so in that case, you are going to have EA minus EI coming from this arc AI. And then you're going to have, again with a plus, EI minus EB. So the important thing here is EI and the other EI, they cancel out if you've got this situation. Of course, the same thing will apply when you concentrate on A or B. You know, everything is in the cycle. So the next possibility is to have, for example, a plus here, a minus here. Okay? If this is the situation, then for this arc you have EA minus EI. This one is minus, so you're going to have EB minus EI, EB minus EI. And of course, that EI and this EI will cancel, okay, again. And the last possibility, or maybe there are more possibilities, I don't know. You may have minus here, and you may have, again, a minus and a plus here, but you can just argue the same way for all of them, okay? They are quite similar, so I'm not going to do it. So anyway, you always get a cancellation for any particular node, and this applies to any node, so they all cancel out, and the end result is a 0, okay? All right, so what is the conclusion here? Any subgraph, any spanning subgraph having m-1 arcs, if it contains a cycle, it has linear dependency. Okay? So, a submatrix B of A that has n-1 columns from A has n-1 linearly independent columns if and only if it corresponds to a spanning graph, spanning subgraph that has no cycles, spanning tree. If and only if it corresponds to a spanning tree of the original graph. Okay? That's the major conclusion we obtained here. All right, so trees and basis matrices, they are the same thing. Or even though they are different objects, they are in one-on-one correspondence with each other. In the example, we had these nodes and these arcs. That was your G. And if you isolate, for example, a tree, a spanning tree, I don't know, maybe this one. This is a spanning tree of this guy. Okay. Now, if you look at the B matrix associated with the arcs of this spanning tree, you've got arc 1, 2 here, then arc 2, 3, and then 2, 4. Of course, you've got one too many rows, okay? So you're going to have to drop a row. But let's just write down the columns first. 1 minus 1. 2, 3 has 1 minus 1. 2, 4 has 1 minus 1. That's your matrix. So suppose you drop this. When you drop it, you've got the upper portion of the matrix. So this just goes, okay? Which means you're dropping a node here. You've got arcs, but you dropped a node, okay? So you've got linear independence here. You can see that that is the case. Did I write them down correctly? Okay, 1 minus 1, 1. Well, this one is gone now. Okay. Yeah, this is correct. It's a basis. So what you see here is a basis. Without that, if you had, for example, instead of a tree, if you had a cycle, you would not have a basis. Okay? So let's return to the minimum cost flow problem. Defined by the flow conservation equations, defined by the node arc incidence matrix, where A is m by n, rank m minus 1. Okay? Now, this row dropping is not pleasant. If you want to work with the simplex method, you don't want to deal with which row to drop and things of that nature. So there's a convention to do this which is an easy way out, what they do is they take the initial graph, they add a node labeled, say, m plus 1. So it's m plus 1. Well, I'm adding it, but I'm also going to drop it later, okay? So this is just a tentative situation. Add a node m plus 1 and arc, say, m to m plus 1. So we expanded the network by one arc and one node. That's what we did. So if the original graph was defined by, say, G and NA, then you have now an expanded graph. Let's call it, say, tentatively N star and A star, okay? Now, you've got A here. If you look at the node arc incidence matrix of this graph, how many rows does it have? Well, what's the rank of it? It's going to be m, okay? So, A star, I'm not going to call it star yet. Let me call it A tilde first, okay? I'm going to take the A matrix of the previous one, and to it I'm going to add a new row corresponding to the new node added, and there's also a new arc here, m plus 1. So we expanded the row space by 1, expanded the arc space by 1. Okay, we added a column, we added a row. Now when you did that, the first portion corresponding to original rows 1 through m and original arcs, whatever they are, is defined by A. Okay, so you preserve that. Over here, what do we have? Well, over here, none of these arcs touch here, so this is a vector of zeros here. Over here, we have a plus 1 in position m here. Okay, so there will be a plus 1. So we're talking about the unit vector em, which has a plus 1 in the mth position. Here, what do I have? M minus 1, yes. I have a minus 1. And rank of A tilde is obviously m. Okay? And I'm going to drop this. So we don't really work with the exactly expanded one. We drop the last node, and when you drop it, the resulting matrix, which I'm going to call, say, A star, has the look of A and EM, with EM tagged as a new column at the end. Okay? The row is dropped. All right. The rank of this is still m, because you deleted a redundant row. We work with this. We work with this, but I think it's time to take a short recess, maybe 10 minutes at most, and then we return to our arguments here. Okay?